Thank you. Thank you, Subhro. First of all, I'd like to thank Subhro and Sergej, who's not here apparently, for inviting me to give this series of 2 lectures. And the goal actually will be to explain how to go from the notion of fusion category, which looks pretty abstract, and don't be too worried about that. I will try to avoid the categorical language as much as possible. And then to show you how we can connect this fusion category to Anyon theory. So it will be sort of long travel from fusion category to Anyon theory. Okay. And first of all, I think it's fair to emphasize that all this story really started in the late 70s, in 1977, where Linus and Miriam realized that in 2 dimensions, one could have some exotic excitations, which have been then dubbed anyons. And this anyon theory really became popular in the 80s after the discovery of fractional quantum Hall effect. And it took a lot of time to understand what was the proper language to describe them. So, of course, there are also several people who have been working on that. So usually people have to talk about Michael Goldin, Menikoff, and Sharp. And if you're a bit interested in the history of Anyon, I strongly recommend you to read a very recent paper by Goldin, published in SciPos in 2023, where he explained how all these ideas really showed up in the late 70s. And then a couple of years afterwards, the name anyons was given by Frank Wilczek, having in mind that anyons mean any-on in the sense that these are excitations, collective excitations, which can have any fractional statistics. Of course, this is not completely correct. If I have time, I will explain to you that not anything is possible, but only part of it. And the underlying idea about all this construction is that if you think about the braid group and the proper description of a braiding property, which is usually used to describe anyons, in 2 dimensions, it can have some non-trivial representation. Okay? So if we have abelian representation of the braid group, we will have abelian anyon, and if we have non-abelian representation of this group, we will have non-abelian anyon. So this was the original way that those set of people thought about it. Then Frank Wilczek developed this notion of flux charge composite, which allows also to understand abelian anyons in terms of Aronoff-Bohm effect, where you have charges and fluxes which can pick up non-trivial phases. But that's the way it was really originally explained. So then in the 80s, okay, as I was explaining, we had this discovery of fractional quantum Hall effect. And then the anyon switched from a purely theoretical point of view to experiments. Okay, so people started to be more and more interested in the field. And as most of you know, so this was the experimental part, but then there has been all this bunch of wave functions, the most famous one certainly being Laughlin's wave function. And then many other people proposed different state to describe the fractional quantum Hall effect. Right, and at the same time, still in the 80s, which is sometimes considered as the golden age of condensed matter, the discovery of high-TC superconductors also triggered much attention in the community, and many people like Phil and Destin, for instance, propose to have sort of non-trivial description of those states, the most famous one being the RVB states, which has some interesting feature in the sense that they do not break any symmetry, but still contain some non-trivial sort of order. So now this is a prototypical example of what we call the topologically ordered state. And at the same time, there was also this notion of chiral spin liquid, which arrived in the late in the late 80s. And to understand why we could have different sort of states which do not break any symmetry, at least in the usual sense. Well, I mean, local symmetry, of course, today, and especially in this workshop, we will think that it's still some symmetry broken state, but with higher forms. But at that time, people didn't have that in mind. And then in the early 90s, Wen introduced this notion of topological contour model, so which will be at the heart of what I will explain today. Topological contour model. And in this context, at least what I will discuss today, this will be almost completely equivalent to say that we have Anyon theory. Okay. So in the 90s, people started to realize all that from the physics point of view. Of course, there has been also many developments from the mathematical point of view. I will flash a couple of them afterwards. And similarly, Sergej, Sergej, the same time also had this idea that some Z2 spin liquid could be relevant to describe some states associated to this chiral spin liquid. Well, although the Z2 one is not a chiral spin liquid. And then, okay, people say, we have states, we don't know exactly what they are. They have some interesting property. Now, we can interpret them in a more modern language, like saying that we have long-range entanglement. But I think the next breakthrough was really in 1997, where Alexei Kitaev introduced this famous paper about Tori code with the idea that we could use this Anyon to perform topological quantum computation. Or in the first step, it was essentially topological quantum memory, but and then this idea of Anyon really became more and more popular because, first of all, the paper by Kitaev really introduced a very simple way to understand what was Anyon, although it was restricted to a very specific set of anyonic theory. And at the beginning of the 21st century, now many people started to develop this notion of category language to understand exactly what was a proper tool to analyze this anyonic theory. Okay, so as usual, when we have some new physical concepts, we need some new mathematical tools. So obviously it doesn't work exactly this way because the mathematical tools were still here, but for physicists, it took some time to realize that this was a proper language to describe, yeah, Benoit. Yeah, so that's the next step. So this was really the condensed matter description. Yeah, so I fully agree. So I wanted to put it in the mathematical case. Yeah, I agree. So as Benoit was saying, so this was essentially the viewpoint of condensed matter physics, but at the same time in the late 80s, especially in 1989, people like Ed Witten, Moore, Seiberg, Berlinde, and coworker, of course many other ones, introduced this notion of topological quantum field theory, and also rational conformal field theory. And as we might see, this is obviously deeply connected to the Anyon description, right? There are certainly many other things to say. I agree with you. Yeah, of course. So he knew, of course, all those things when he introduced this notion of. They require new mathematical tools. Okay, so it's not a row. It's okay. You need some new tools to describe some new results in physics. Okay, to have the proper description of that. And this is essentially what I will introduce today. Okay. Right. So from the high energy physics part, there was that. And also from the math community, there are also some links with a knot theory. I will not discuss all that, of course, today, essentially due to Vaughan-Jones, who was also deeply involved in this business. And but being able to connect all these things really took some while, and I think it's fair to say that all that only arises in the last 20 years, essentially. Okay. Right. So what are the new tools that we need to describe those anyons? This is precisely the heart of this series of lecture. So we will need this notion of fusion category. So fusion category is a very broad topic, but as I will try to explain, so I will essentially focus on what we call unitary fusion category. It's called UFC. Okay. And this is not sufficient to describe Anyon theory. I will give you the ingredients that we need to have a proper fusion category. But those fusion category, there are, of course, many different types. Some of them may have non-commutative fusion rule. I will explain to you what it means in a second. And this set of fusion category will not describe Anyon theory. If we want some Anyon theory, we need commutative fusion. But this is, again, not sufficient because as I explained at the very beginning, when we talk about Anyon, we want to have this notion of braiding, which is well defined. Okay, so some of this commutative fusion category will be non-braided. And this one will not describe Anyon theory, so we need braided fusion category. Braided UFC with commutative fusion. And this again will not be sufficient. We need an extra layer, and this will be the last one, because some of them might be what we call usually non-modular. And modular and non-modular will be precise also in a second. So this one will not be the proper one. And the good one will be this one, which are called unitary modular tensor category. And this UMTC are the proper one to describe Anyon theory. Okay, so there was an equivalence here between topological quantum order, at least in the sense that I will discuss today, this notion of Anyon theory, and this again will be completely equivalent to UMTC. Right? So if you have any question, don't hesitate to interrupt. For the moment, it's kind of introductive, but so my goal will be to take you from here to there and to explain to you what are the subtlety on the way to connect UFC to UMTC. Yeah, Frank. Sorry? If you have Anyon, you want them to be commutative. I mean, if you want to fuse A and B, you want that they fuse the same way as B and A. Vec G does not describe Anyon theories if it's G is non-abelian. The Drinfeld center of Vec G will, but the Drinfeld center has some commutative fusion. Okay. So for those of you who knows nothing about category theory, let me just say very few words about that before coming to the fusion category language. So the category theory was developed in the 40s and introduced actually by Eilenberg and MacLean in a series of 2 papers. So of course, I will not follow the mathematical description. I just want to tell you what exactly the way they define a category. So they say that the category is an aggregate of abstract elements called the object of the category and abstract elements called mapping of the category. So some people sometimes say that this simply amounts to say that a category is a set of points connected by arrows, which are called morphism. But this will not be very useful in our case. We need definitely some more structure, and that's exactly what I will start to explain right now. I'd also like to mention before starting more concrete things that if you want to learn a bit about all that in a very sort of complete framework, I think the best introduction is the book by my friend and colleague, Steve Simon, called Topological Quantum, which was published in Oxford University Press in 2023, if I'm not wrong, something like that. And of course, if you want some more mathematical information or more dense thing, you may also have a look at the famous paper by Alexei Kitaev, published in 2006. So this paper is especially famous for the Kitaev honeycomb model that many people knows. But actually, I think the most interesting part is definitely this famous Appendix E, where he gives this algebraic description of Anyons. Okay. So if you ask a nasty question and I don't have the answer, for sure, they will be contained in the book by Steve with a high probability. Okay, so what are fusion categories? So to define a fusion category, we need 3 things. The first thing are called the objects. So this is, again, the mathematical language. For physicists, usually we call them particles or super selection sectors. And at the end of the day, when we will deal with fusion category, which are actually UMTCs, this will be simply our Anyons. Okay, so if you think about the toric code, okay, this will be my 1, E, M, and epsilon N. Then we need to give a set of rules, which are called the fusion rules, which will tell us how this object fuses. I will come back to that in a while. And these fusion rules are usually encoded into some matrix, which are called N. And sometimes this is simply called the N symbol. But these are just the fusion matrices. Okay. And then the third thing that we need is a set of symbols called the F symbols, which stems from the associativity of the fusion rules. Okay? So when we are dealing with category in general, we need a set of consistency rules. And these F symbols that you might have seen in many papers, they simply stems from the fact that the fusion rule have to be associated. So that's basically it. I also want to point out that this set of objects has to be finite. So I will sometimes use the notation n, which will be the number of objects in my category. And n has to be finite. Okay, so it's also called the rank sometimes of my category C. So it's C. Okay. And it has to be finite. Okay, so what are those fusion rules? So I will use the notation for the object in the following. So objects, I will call them with letter like A, B, C, blah, blah, blah. And there will be n of them. Among those objects, there is also a special object, which is called the vacuum. Okay. Vacuum. I will note it 1. It's not the same one as above. And it has a special property that it fuses trivially with all other anyons. So now I have to explain what is the meaning of this, this fusion. So suppose I have an anyon A, and I want to fuse it with an anyon B. So what does it mean? It means that physically, you may think about it as I have one particle somewhere. I take another particle. They are bound by some sort of interaction, although this notion does not exist here. And I just ask the following question: what are the properties of this composite object of A and B? Okay, so physically, fusion simply means I have to think about it as I glue them together, and I want to look at the property of the composite object. So sometimes I will represent this fusion by 2 points. Okay, so here I have an anyon A, I have an anyon B, and I ask the question, what is the global property of this object? Okay, and it turns out that these fusion rules can be written in this way, so that's why they are encoded in the fusion matrices. It will be a sum over C of numbers, integer number, n, A, B, C, anyon C. So what does this mean? These are the fusion coefficient. Okay. And they should be seen as the following. So if A and B can fuse to C, okay, then this object is different from 0. And if they cannot fuse to C, then NABC will be equal to 0. Okay, so NABC equals 0 if C does not belong to the fusion product of A and B, and otherwise it's non-zero. So here we have to distinguish several situations. Sorry? No. They are positive integer, okay, but they can be larger than 1. So that's exactly what I was about to write now. So and ABC are integer number. Okay. And if all n ABC take value only in 0 or 1, we will say that the category has no multiplicity. Okay, so we'll say that C is multiplicity free. Okay, and in some cases, it can be larger than 1, and then we will say that we have some multiplicity, right? That's a simple definition. Yes.
It's not. What is the meaning of the plus sign? The dimensions of the space add.
It's just no. They don't add. No. It's not a direct sum. It's just a way to say that. Well, it depends. Yeah, but from the physics point of view, it means that if you fuse A and B, they can behave either as C or as C prime or as Z. Okay. So indeed, in the categorical language, I should write this almost like a tensor product, and this like a direct sum. Okay.
Let's say I didn't know this about that. Started with a vacuum.
Yes.
And I told you that I know it's the form of an operator created.
It cannot be created alone, but okay, you have to create a pair of Anyons, yes.
So that operator I know.
Uh-huh.
Now to create a different state, I actually need to put the whole sum. And there's a well-defined meaning of the product. It's okay. Now I put back to an action product of all subsystem.
Yes.
The right hand side. What does it mean that it's simple? Does it mean I have?
It means that you will have a sort of superposition of two states. If you think about it in a quantum mechanical way, you could have a pair of AA bar plus a pair of BB bar. This will be the action if you act with your operator onto the vacuum.
That's the left. What is that? What is the right side? Does it mean I have direct sum?
Somehow, yes. Yes, you can think about it in this way. They will belong to different spaces. Okay. Actually, when I draw this kind of picture, okay, and AB, let's say they fuse in C, you can think about this drawing as a sort of cat, where I have Anyon A and Anyon B, which fuses in an Anyon C. Okay, and this will be a sort of orthogonal basis for different ABC. Yes, yeah. It's a different state, completely different state. For non-abelian Anyon, you can still have several possibilities, yes. I think many people tried, but I'm not aware about anything which works. Yeah. Well, actually, you have a fusion category which can be built with representation of a group if you wish. This is part of the setting, but okay, no problem.
There is a question
Online.
yeah, online. Can this NABC be really thought of as a Clebsch-Gordon?
No, they are not the Clebsch-Gordon coefficient. The Clebsch-Gordon will rather be given by these F symbols, because they will tell you how to switch from one basis to another basis if you want to make basis changes. I will come to that in a while. Yeah.
Can I ask?
No, unitarity is also different. That's an extra property of the F symbols, which have to be like unitary matrices. Yeah, so it's semi-simple. Those categories are semi-simple, rigid, monoidal, and all that, but I don't want to enter into this language, but precisely. Okay, so now we can come to Andrei's question. We must also, so we distinguish the case where we have only 0 and 1 for the fusion coefficient. If we have some coefficient larger than 1, we will say that we have some multiplicity. If we don't, it will be without multiplicity. We also have a more important case where when we fuse A and B, we have a unique NABC, which is non-zero, okay? So unique, non-vanishing NABC. And if we have this kind of fusion rules for all Anyon ABC in my category, okay, my fusion category, this will lead to the notion of abelian Anyon. So this is a definition of abelian Anyon. Okay, it's a Anyon theory, so a fusion category for which we always have a unique fusion outcome when we fuse two objects A and B, right? So what does it mean? It means, and to come back to Andrei's remark, that if I take Anyon A here and Anyon B here, I know exactly the way this composite object behaves. It can only behave in a unique way, C, right? And if I have different fusion products, so suppose I have one fusion rules, which is like A cross B gives C plus D, okay? Then I will have non-abelian Anyon. Non-abelian. And this tells me that giving you the value of A and B is not sufficient to fully describe my state. I also have to specify the way they fuse, and they can indeed fuse in different channels, C and D. So the remark by Benoit only holds actually when we have non-abelian Anyon. If it's abelian, we have the whole information. Right? And that's the most puzzling part of the game, because usually if you think about, okay, as I was explaining, there was this nice picture with a composite flux charge. And in that case, this only essentially leads to the picture of abelian Anyon, because think about a magnetic flux. If I give you a magnetic flux in one region, magnetic flux in another region, and I ask what is the overall magnetic flux inside a bigger region, just the sum of both. So there is no issue about that. With non-abelian Anyon, we can have more subtle things.
Julien, can I ask one question?
Sorry?
I am online actually. Can I ask a question? Can you hear me?
Yeah, I can hear you, yeah.
Yeah, well, how do I see that NABC need be integer, and what is the rationale behind NABC to be integer?
So, okay, there are several ways of looking at that. So first of all, for all consistency relation I will explain, we need them to be taken as integer. But the main information that NABC contains is simply to answer the question is, if I have an Anyon A and an Anyon B, can they fuse in an Anyon C? And in this case, if we forget about this multiplicity issue, I will say that NABC equal 1. It's really a definition of my fusion coefficient. And if they cannot fuse in C, I will say it's 0. Okay. So as someone was explaining, think about you take when you want to compose two spins half, okay, you will say it's 0 plus 1. Okay, they can fuse. So think that this 1/2 is an object, A. If I fuse it with the same object, 1/2, they can fuse either in 0 or in 1. Okay. But you may still ask, why do I put a 1 here and why do I put a 1 here? I could put some non-vanishing numbers, but there are some sort of normalization and just the idea that it's just a way to encode the information that they can fuse indeed in this channel or in this channel.
Yeah, thank you.
Is it fine?
Yes, thank you.
So among important information also for the fusions, because at this stage we are still at the fusion stage. So each object, A, has a dual object, usually called A bar. So this is a dual. Yes, you can think about it as a generalization, but it's a very broad generalization of group theory. So precisely for group theory, it essentially corresponds to abelian Anyon. Okay, but in that case, you can have different products. So imagine that you multiply a group element with a group element. It can be decomposed into a series of elements. So sometimes in the categorical language, we say that this is not you have a simple object. So my A, B, C, they are simple. They cannot be decomposed in further object. But this is a sort of composite object. It can be decomposed in simple objects, which is not the case for groups. Okay. Right. So what means the dual of A? It means that in a fusion category, I will always have for each object A, if I fuse it with its dual, okay, A bar, they can fuse to this very special object, which is a vacuum. I will give the property of the vacuum, plus maybe other components. Okay, so the only way to annihilate, if you wish, your Anyon A is to fuse it with its dual, and then you will get the vacuum. The vacuum is nothing. It's like, as you were asking, the neutral element for a group. Right? And this vacuum has a property that if you fuse, obviously, the vacuum with any particle A, it gives you. So if you have non-abelian Anyon, they have to fuse in the vacuum because that's the definition of the dual, but they can also fuse in other channels. So if you're familiar, for instance, with the Ising theory, where you have a three label, like 1, sigma, and psi, if you look at the fusion rule of sigma with itself, okay, it can fuse into the vacuum plus psi. There are two different fusion outcomes possible in that case. And this also tells you that sometimes the dual object of A might be itself. Okay? The dual of sigma in that case is also sigma. And in this case, if A bar equal A, we say that A is said to be self-dual. I would say yes. Maybe you need some extra constraint for the OBE, but it's essentially what you find in the operator expression. For every A, there is a dual object A bar. Yes, so that if I take A and A bar, I know that this is a valid state. They can fuse into the vacuum. That's the definition. And this exists for all objects. And there is a unique A bar, yes. There shouldn't be what? No. There are dots. There can be dots. In the example I give here, there are dots. Okay. So, yeah. So precisely. So there is a unique A bar such that A cross A bar gives 1, but A cross A bar may also give other objects. So if you have no dots, you have no dots. So it means that when you fuse A with A bar, you have a unique fusion outcome, which is a vacuum. So for a group, indeed, you will always have that. Okay, but also for many other theories. So if you think about toric code, for instance, that we've heard a lot about these last days, if you take E cross E, it gives you 1 also. Okay. And even in the Ising theory, so in this case, we can have several results. But if I look at the fusion of psi with psi, it's also, there is a unique, there's only the vacuum in this case of this theory. So in the following, and to make things as simple as possible, I will focus on theory which are self-dual. Okay, so from now on, I will essentially focus on theory, self-dual theory. So self-dual category means that all objects it means that A equal A bar for all objects. Okay, and I will focus on this set of category just for simplicity. And I will also focus on multiplicity free category, which means, again, that N, A, B, C only equals 0 or 1. But one has to keep in mind that there are more complicated theory which can be of interest. Okay. So one important property of this fusion matrices, so now we come to point 2. We are still in the fusion rules. So remember, we had 3 points. The first one was objects, fusion rules, so N symbols, and F symbols, which will be the last thing I will have to discuss. So this is all we need to define a unitary fusion category. So a very important property of these fusion matrices, so the fusion matrices, I denoted them by NA, and their matrix elements were NABC. So that's the way to read this fusion coefficient. If I fuse A with B, if I have a possible outcome C, it will be 1. If not, it will be 0. So my fusion matrices NA will have elements BC. This is what I denoted NABC. And the nice thing is that the fusion matrices, they obey NA times NB, sum of the C of N, A, B, C, and C. So they obey the fusion rule. And in this case, the fusion, which was indeed sort of tensor product, is now the multiplication of matrices. And here we have the fusion coefficient. Okay, so that's one property of this. Yes. It can. Well, You can prove that this holds. So indeed, the NA and the NB, when you multiply these objects, they have only, in this case, they have only entry, let's say 0, 1. But then the product of these two objects will have a larger integer as entries. And that's why you can also have them here when you sum them. And so this has a direct consequence, is that if A and B, so if we have commutative fusion rules, so of course, I didn't define what we call commutative or non-commutative, but it may sound a bit trivial, but okay. If we have A cross B equal B cross A, we say we have commutative fusion. And if these two objects are different, we have non-commutative fusion rules. And for people entering in the field, of course, sometimes it's a bit confusing because here I discuss the notion of abelian and non-abelian, but it's not related to the notion of commutative or non-commutative fusion, contrary to what we have in groups. Okay, because we can have some commutative fusion rules giving rise to non-abelian Anyon. That's exactly what happens for the example I gave here. For the Ising theory, we have 3 Anyons, 1 sigma and psi. If I fuse sigma with sigma, it's obviously equal to its dual, but still sigma is a non-abelian Anyon because it can fuse with itself into different channels. Okay, so the notion of abelian and non-abelianness for Anyon theory, or in general for objects in a fusion category, is not related to the notion of commutative or non-commutative fusion. That's definitely not the best way of saying things, but that's the way it has been introduced in the literature. Yeah. So it was like a one-dimensional representation of the brain. Yeah. But at this stage, I didn't. Yeah. But at this stage, I don't even invoke any braiding considerations. So, but that's the way. Yeah, that's where it comes from. It's a good reason, but it's a bit confusing sometimes. Okay. And so, as I was explaining also at the very beginning, of course, since we want to go from this very general unitary fusion category framework to the very specific one which describes Anyons, for Anyons, and this was a question by Frank, I want A and B to be equal to B and A, because of course, physically, if I take two objects, A and B, I want them to have the same property as if I take the object B on the left or B on the right and A on the left and on the right. Okay, so the only fusion category which will be reliable description of Anyon theory will have some commutative fusion rules. And this is maybe still on the, no, I erase my general diagram, but I will essentially focus on this. And so this has a very important consequence, because since the fusion matrices obey the fusion rules, it also means that if I have commutative fusion rules, my fusion matrices NA and A and B do commute. So that's an important property. And we can also show easily that NA commute with its transpose. So NA are called normal matrices. And so we can diagonalize all these NAs simultaneously with a unitary transformation.
Could you proceed? So since you wrote this direct product of spin halves. So one way to think about that is basically these are the representations of SU2.
Yes.
And you're doing a
absolutely.
decomposition of product of representation.
Yes.
Is there a notion of a group and the thing that you just erased, A cross B, A and B being representations of some G?
Yes.
And
So
A and
one
B.
fusion category is a fusion category built from representation of groups.
Okay, so
this is one example of fusion category.
Anyons as representations of some.
Not yet, because again, this is at this stage we are just dealing with fusion category. When we want Anyon, we need more information. We will need the braiding and all that. For the moment, everything I'm saying for the moment, usually, okay, maybe sometimes I'm talking about anyons for A, B, C, etc. But at this stage, these are only objects of the fusion category. Mm-hmm. They will only become anyon once I have a unitary modular tensor category.
Sure.
Yeah. Yes. Yes. Yeah, but I also say that I also explained that the fusion matrices, they obey the fusion rules. So you have also NAB, NA and B equal NB and A, so they commute. So there exists a unitary U such that NA equal U, a matrix, a diagonal matrix, and lambda A, U dagger, and U does not depend on the A, so they can be simultaneously diagonalized. All right. So let me rewrite this in a slightly different way. It can also be written this way. That's right. And we will see that this has a very important consequence. So first of all, if I write this identity for a given element BD, can be written as follows. So it will be a sum over C of N A B C times my unitary U C. Okay, so this is a matrix elements BD of the left-hand side. And this equals U B D times lambda A matrix element DD. Okay, so lambda is a diagonal matrix. Huh? So far, so good. Nothing really interesting. But now, it's worth considering the very special case where we take the element B to be the vacuum. So we set B equal 1. Okay. And in this case, we have NA1C, which by definition equal delta AC. Is that clear? So again, this gives me the information about what happens if I fuse A with the vacuum 1. And since 1 is a vacuum, C has to be equal to A. Otherwise, it's 0. So now if I plug this identity into this equation, I have the following. I have sum over C of N and 1 C U C D, which is equal to U A D. So, sorry, this is a direct consequence of that. So this is one way to compute this quantity. And the other way to compute it is to come back to that. And so this will also be equal to U1D times lambda A D. Okay, nobody complains? Okay, so this identity just comes from this, and this relation comes from that, where I set again B equal 1 in the game. Okay, so this gives me directly that the quantity, so the eigenvalue lambda, so this eigenvalue of lambda A is given by the ratio of U A D divided by U1. Yes, that's one important relation. And now let's try to compute another thing, which is the more general coefficient NABC. So NABC will be, so now I use this relation. Okay. It will be a sum over two indices, D and E, of U, B, D, lambda A, D, E, U dagger, E, C. And now if I use this expression for lambda A, DD, and I keep in mind that D has to be equal to E because it's a diagonal matrix, I'm led to the final formula that I wanted to derive. Which tells me that the coefficient NABC can be written as follows, as a sum over D of UBD D times U A D over U1D. Okay, this is just my lambda ADD that I have obtained here, times U dagger EC, which is actually the same as U star C D because D equals. And this very important formula is known as a Ferlinde formula. Okay. And so for those of you who are familiar with Anyon theory, usually this Ferlinde formula is not derived in this way. And some of you may have noticed that this U matrix, which is here defined as a unitary which diagonalizes the fusion matrices, will become at the end of the day, and if I have time tomorrow, the S matrix, which is usually used to derive this, this expression, which encode mutual statistics, mutual braiding of.
Can I ask a question?
Lambda, that's a diagonal matrix, just the diagonal matrix which contains the eigenvalues of NA. There will. I'm coming to that now. Yes.
Vijay, go ahead.
Yeah, so how do I know that I can diagonalize this N matrix?
I explained it here. So first of all, I consider the case where the fusion rules are commutative, which means that NA commutes with NB, okay? Because again, the fusion matrices, they do obey the fusion rules. And secondly, one can also prove that NA commutes with its transpose. It's a simple exercise.
Thank you.
So this means that the NA are normal matrices. And if you have a set of commuting normal matrices, you can diagonalize them simultaneously.
Okay, thank you, thank you.
Okay, now maybe it's time to switch to your question, Andre. So indeed, we have seen that the NA, they obey the fusion rules. So let me write it down again. We have NA and B equals sum over C and ABC and C. And now if we consider the largest eigenvalue of NA, this is called the quantum dimension of the Anyon A. And obviously they also obey fusion rules. So let me introduce dA, which is the largest eigenvalue of NA. This is defined as a quantum dimension of A. And since the NA obey the fusion rules, that's the same for this largest eigenvalue. So we also have indeed dA times dB. Now it's really a multiplication of number, which equals sum over C of NABC. BC. I think it's unique. I don't know if I can prove it easily, but yeah, I don't know. It's a good question. I think it's a unique largest eigenvalue, like a sort of Perron-Frobenius eigenvalue for these matrices which are made of only positive integers. Yes, they are numbers, but they can be any sort of numbers. They don't have to be integers in this case. They are also? No. A and B. They are okay. So it's the indices. These are indices of it's the index E, index A. Yeah. So wasn't it? Okay, so get rid of that. So this is D in this A. Other question? No? And once we have this quantum dimension, usually we also straightforwardly introduce the so-called total quantum dimension. So there are several definitions in the literature, but I will use this one. So capital D, which is the square root of the sum over all quantum dimension square. Okay, this will be also an important quantity in the following. So now you can immediately see that another way to define abelian theory. So for abelian anyons, they have a quantum dimension dA which equal to 1. This is pretty clear because if I have dA times dB equal dC, for all ABC, the only solution is to have dA equal 1 for all of my anyons, given that these are also the eigenvalues of these fusion matrices, right? And for non-abelian anyon, dimension will be strictly larger than 1. So for instance, if I come back to this Eyring theory, where I have 3 objects, 1, sigma, and psi, maybe I should write all those fusion rules somewhere. So I have, of course, A cross 1 equal A for all A. That's my vacuum. Then I have sigma cross sigma equal 1 plus psi, and psi cross psi equal 1. So these are the 3 non-trivial fusion rules. They are commutative, so all of them are given there. And so you can directly see that the dimension of the vacuum D1 is always equal to 1. This is completely general, okay, because I always have A cross 1 equal A. So dA times D1 has to be equal to dA. So D1 is always equal to 1. And for this special case, which is known as the Eyring UMTC, but I haven't yet said what is a UMTC, but okay, let's stick to the fusion. I have also d psi equal 1 and d sigma in this case, which is equal to square root of 2. Right? You can check square root of 2 times square root of 2 equal 1 plus 1, etc. So, of course, you may ask, why is it called a quantum dimension? Does this word has any meaning? And what's the physical way of understanding that? So what is nice is at this stage, I will explain this the physical meaning of the quantum dimension. But at this stage, you see that the only information that I have used for the moment is just the fusion rule, nothing left. I didn't ask any further structure to my category. I just have a set of objects, a set of fusion rules, and that's all. I just require the commutativity of my fusions, but that's all. And out of that, I can already derive this Verlinde formula, which will become important maybe in the next lecture tomorrow. Yeah. And that's what I wanted to emphasize. So what's the physical meaning of this quantum dimension? So suppose that I have, again, in this sort of globular vision of fusion, I have anyon A, which fuses with another anyon A. And I ask, how many states like this do I have? Okay. So I don't know exactly. It depends on the fusion rules of A is A. So again, if I stick to self-dual theories, they can fuse into the vacuum, but also in other objects. But now suppose that I fuses these two with a third object, A. Okay. And then I fuses these 3 objects with a 4th one, and so on and so forth. And at each step, you look at the large limit where I fuse n anyon A together, and I ask how many different states do I get? And you can see, because this is precisely the definition of the largest eigenvalue of NA, that the number of states, number of different states, scales like dA to the power n. So it's like a sort of dimension of a local Hilbert space in which you would fuse many objects together, and you want to ask, how does my Hilbert space scales when I consider n particles of the same type? Okay. Okay, so there is another representation of that I may introduce right now. let me now introduce what we call the fusion trees. Also important. It's just another way to represent that, but it will be useful in the following. So what is a fusion tree? So it's just a way to represent this in a diagrammatic manner. So what do we do? Usually in a tree, we have some branch. So let's consider branch A, the branch B, the branch C. And we ask the following question. When I fuse A with B, okay, I have, for instance, A cross B. Let's say they can fuse in D plus E plus blah, blah, blah. So suppose I have a state where A and B fuses into D. And then I want to fuse A and B with a third object, C. And it amounts to, as the question, how C and D fuses together. And let's assume that C cross D can fuse in F plus G plus blah, blah, blah. And let's assume that I pick up a given channel F. This will be represented by such a fusion tree where A and B fuses in D and C and D fuses in F. Okay? So these are just two different representations of the same state. And in the following, I will need these three representations. That's why I want to. Yes. Yes. Absolutely. Yes. So this is one state. But if I have such fusion rules, I will have indeed another state where A, B, C may fuse also in E, for instance. And then I have to specify like C and E, suppose they fuse in, I don't know, let's a unique channel H. So this will be another state. Okay. So now we have to discuss the last point, which is important to define the fusion category. And it has something to do with the associativity of the fusion rules, which is something I haven't discussed so far. But what's really important is to keep in mind that these fusion rules, they have to be associative. So what does it mean? It means that if I fuse A with B first, and then I fuse this with C, it has to be equal to fusing B with C first, and fuse it with A. And this associativity will have a very important consequence. So if I want to represent this as a fusion tree, so first I was fusing A, B, C. Here I fuse A with B first, and then with C. But it has to be related to another tree where I first fuse this B and C, and then I fuse it with A. Okay, these two things have to be related in some sense. Okay, only because of the associativity of my fusion. And this will lead me to introduce these F symbols, which will be basically the way to switch from one basis, let's say the one for which I fuses first the object from the left to the right, to another basis where I fuses first the object from the right to the left. And to do that properly, we have to draw the following diagram. This will be the end. So suppose, to do it consistently, because it's not fully sufficient, now I consider a problem with 4 Anyon. And I will argue that this is actually sufficient to have a full consistency of this associativity. So I start from a state where I have A, B, C, D. A and B fuses in the channel F. F and C fuses in G, and G and D fuses in E. Okay. And at the end of the day, I want to reach another description of this basis, like this, where I still have A, B, C, and D. But of course, they can fuse in different things. The only important thing is that the overall outcome will be the same, E. So why is it so? It is, again, because suppose I have different objects like this. So how can I draw this associativity? So I show you that it could be either like that or like this. But now if I want to specify the way A and B fuses in the given channel C, and the way C and D fuses in the given channel F, I have to give you slightly more information than just this associativity. So all I want to say is that suppose I have three anyons, A, B, and C, and I want to describe the states of A, B, and C. The only important information is what is the overall fusion outcome of these three objects. Okay, and it should not matter whether I first want to describe them like A, B, C, or if I give you another information about B and C, which fuses is in something like E, but then E and A, they have to fuse into the same channel. Okay, because globally, this gives me the overall information about what is the behavior of the composite object ABC. And I don't have to specify whether I want to describe it by first fusing A and B first or B and C first. Yes? Sorry? Yes, it's a sort of physical demand, but it's actually just a way to understand physically what means this associativity. Well, I just mean that ABC, if I write these fusion rules, I don't have to tell you whether I first consider the fusion of these two things or these two things. This is a unique object. So meaning that this is a unique object means that A, B, and C will fuse in a unique fusion channel. Yes, I asked that associativity is here for a fusion category. My fusion rules have to be associative. They may not be commutative, but I want them to be associative. Why? So for a fusion category, the fusion rules have to be associative. They have to. Otherwise, you violate some axioms of the category. So it has to be like that. Now, what I'm just trying to argue is how to understand it physically. What does it mean? It's axiomatic. But if you accept this idea that fusion just gives you the property of the composite object, I give you a composite object of three objects, ABC, and I look at what is this object ABC. And this does not depend the way I describe it in the box A, B, and C. Yeah, but we are on the blackboard, not in real life. No, it will enforce some constraint that I'm going to write down here. Okay, so how can I go from here to there? I can go in one direction by first instead of fusing A and B together and C and D afterwards, I can fuse them in a different way. So I can do this. Okay, so A, B, C, D. So A and B, they always fuse to F. So this index will be fixed once for all, okay? A, B, C, D, F, G, E. They will not change. But now I ask the question, what happens if I fuse C with D? So they can fuse in something different. But again, I ask that the overall fusion outcome is the same, E. Okay. And then I can go from here to there. So here, to go from here to there, okay. I should have introduced something which is actually written here. So if I have an index D here and an index E here, if I want to go from this description, sorry, let me do it properly. Skip something. If I want to go from that basis to that basis, right? So here B and C will fuse in F, and again the overall channel. This is related by a transformation. And yeah, I ask this transformation to be unitary. So it will be a sum over some coefficient, which will be my F symbols. Right there, these F symbols. So these F symbols, they will depend on A, B, C, and E. Okay, so I will note them A, B, C, and I will put the E here. Okay. And they will also depend on D and F. Okay. So these F symbols, they have to be understood as a matrix. So F, A, B, C, E is a matrix. And this is like a basis change from this description, where I first fuse the object from left to right, from another basis where I fuses my object from right to left. Okay? And the entry of this matrix here is DF, where D is this entry, where I first fuses A, B into D, and F is this entry where at the end of the day, B and C fuses to F. Is that clear? So now the question is, how do we determine these F symbols? And that's exactly what I anticipated here. And I hope I will have time to complete this, this diagram. So just to say that if I want to go from here to there, I need the following F symbols. So I need F. So I did a sort of F move of F, C, D, E, index G, and fuses in L. Okay, so this is the F symbols which is needed to go from here to there. Okay, because here I first fuses F and C and then fuses with D, whereas here I fuses C with D and then I fuses it with F. That's exactly the content of this object using this definition. So these are, I don't know who asked the question. These are like Klebsch-Gordon for groups, but this is pretty much likely like a comparable blocks. Yes. Indeed. Yeah, Frank. Like six, yeah, but Klebsch-Gordon in some cases might be. Oh, Klebsch-Gordon, it's also, these are 6J symbols for groups. Yes, I agree. No, you're right. Okay, so this is one way to go from here to there. And from here to there, what I have done, so I had originally, so C and D, I didn't touch them. So I needed A, B, L, E. So it will be F, A, B, L, E. And as an entry, I had a F. And now A, B. So here, I guess I still have L, yes. E is here, and then I have a K index that I have to specify, so it's FK. Okay. So that's one way to go from here to there. And there is another way where I could decide to first fuse B and C. So A, B, C, D, G, E. Let me go slightly quicker now. This is index H. And then another F move, which takes me from this A, B, C, D, index K, H, E. Okay. And then I go here. Okay. So here also I have F symbols, F symbols. I just give you the global structure of this equation. So this is a consistent diagram, which just gives me two possibilities to go from a basis of state described in such a way or to a basis of state described in such a way. Okay, so it will be a complete description, a complete basis, and there is a transformation that takes me from one basis to another. And so because I have fixed, maybe I will do this in more details next time. But so to go from here to there, you can see that all indices are fixed. So F, G, E, L also is still here, and K. So the structure of this equation, because this will become an equation, so this is called the pentagon diagram, because there is 1, 2, 3, 4, 5 summit. And it gives rise to the pentagon solution, pentagon equation, or pentagon sometimes. And what is the structure of this equation? So we have two F symbols. And this is a way to go from here to there along the upper path. I have the product of these two objects. And here I have 1, 2, and 3 F symbols. But if you look at the indices, and I should do it more properly, but I will likely do it next time. There is a sum, there is one indices which still occur in the sum. So it's a sum of F, F, and F. Okay, and the reason for that is that I have to introduce intermediate object H here in between. So there is a sum over H which occurs here. So I could put all indices properly. I will do it next time. But what I wanted to say to end up with this lecture is that this set of equation has to be solved, okay, for each set of indices. So we have 6 indices, 1, 2, 3, 4. This is the definition of my matrix for 6. And for all this set of indices, one has to solve this pentagon equation to fully define our unitary fusion category. Okay. So we start with very simple ideas like objects and fusions. We saw already that we could do a lot of things. But if we want to fully characterize our fusion category, we also have to give the solution of these F symbols. And this means also that sometimes you can have two categories, let's say C and C prime, which have the same fusion rule, but different F symbols. Okay. And the simplest examples of such a category is based on Z2 fusion rules, where we have two objects. Let's call them 1 and S. Okay. So the fusion rules of these two objects is obviously A times 1 equal 1 times S equal S and S times S equal 1. So here you have the Z2 group structure, and you have two solutions of the F symbols. And the first one will give you Z2 category. Well, actually, it's vec Z2, I should call it. Vec Z2. So that's really the category of the group Z2, where all the F are equal to 1. And another one, which will be vec Z2 twisted. So usually we put the omega here, where some of the, well, for which some F are different from. Okay, so if I just give you the object and the fusion rule, I can still have several options. And this is really the simplest example. Okay. And then we will see that when we want to consider braiding on top of that, we could still have several solutions with the same fusion rule, which gives the same F symbol, but different R symbol, which encodes these braiding properties. And all of them will give rise to different Anyon theory. Okay, I'll stop here. Thank you. Yeah, Sergej.
Thanks. Questions?
I have a question. So I have a question about the last example. So this looks like a group which you ended up, right? So which also has associativity and
yes.
And so are you saying that there are two?
So in this case, the F symbols are nothing but the 3 cocycles, okay? And you always have the solution with trivial cocycle, which corresponds to all F symbols equal to 1, and some solution with non-trivial cocycle, which are sometimes called twisted solution. And these are the other solution. This is the other solution.
Okay.
Okay. So it's a sort of extra structure. So usually when you play with group, you don't have really to worry about that. But if you want to have this sort of F symbols and or cocycles in the group language, then you can still have different solutions.
Okay. Where is, because group also is associative.
Yes.
Right? So there should be also some.
Everything is associative here.
Yeah, yeah. So this pentagon equation, for example, follows from associativity, right? So it's
yes,
kind of consistency on these F symbols.
Yes.
So where is the?
But you have different solutions. You have trivial ones for groups and non-trivial one.
Well, actually, that's where perhaps some category theory flavor might be useful. Is that when we are talking about associativity, it's more isomorphism between objects in a category. So,
okay.
So under cocycle conditions, or in fact, the fact that this pentagon is a composition of arrows in a category, and there's the desire to have the composed arrow to be the path independent. So it's a sort of, it's always a pain in the neck to when people say that two objects are equal. What does the equal sign mean? And in fact, those identifications always modulo invertible arrows. And the F symbol is precisely making explicit what the equal sign means.
Okay, I think now I understand. Yeah. So the first one is just a Z2 group, right? The vec Z2, and the second one is a fusion category with this.
These are different solutions of your cocycle coherence.
Right. Okay. Yeah. Thanks.
This is where we had a private discussion with Benoit and you before. So would you call the Z2 fusion rule as the input category?
No. There's no input, no output here. Okay. That's just, I give you fusion rules, a category, and then I have to solve my pentagons, and I can have different solutions of my pentagon, and each of them would give rise to a different fusion category.
But would you call the different solution different UMTCs? So you were not yet.
No, they are not yet UMTCs. They are different UFCs.
UFCs.
Yes.
So then what do you call the initial one where you just specified fusion rule? What would you call that object?
Nothing.
It's not yet well defined.
It's just one data of my fusion category.
Okay.
To fully characterize it, I need three things: objects, fusion, and F symbols.
Yeah, so I'm assuming the S matrix that you have constructed here is the same S matrix from the safety perspective also, which can be derived how Virasoro characters transform under the modular S transformation.
That's exactly the S matrix you're
Let's say if I consider chiral topological order, I know that it does have a safety description at the edge, and we can construct this S matrix from the safety perspective also.
Yes.
And let's say other than the chiral topological order, if I consider other topological order which doesn't have any safety-like description at the edge,
yes.
Can you construct this kind of S matrix for those cases from the safe edge perspective, or it doesn't have any kind of description?
Okay, so for the moment, I only discussed the case of fusion category. I haven't said anything about braiding, about edges, about chiral central charge, about other quantities like that. I hope I might have time to do it tomorrow. But the thing is, the nice thing, and that's why I wanted to give this proof of the Ferlin formula, is that the S matrix that will come when you add some extra structure like modular structure is nothing but the matrix which diagonalizes the fusion matrices of your fusion rules. So it has a lot of very nice property, but you can already think about it as the matrix which diagonalizes the fusion rule. Yeah.
Subhro, can I ask a question?
No, I'm not sure I agree with this. This is really the co-cycle solution, which gives you different, because the fusion rules, they are the same, okay? So these are the fusion of the elements. Now, indeed, you may have different conjugacy class, you have the whole structure of the group, but the co-cycles, they do encode a different sort of information. Okay, so the co-cycles, the F symbol, let's call it like that. For group, it's nothing but the three co-cycles. Yeah. Yes. Yes, it's easy to prove this. Yeah. You just take the definition of NABC and you can prove that they fulfill the fusion rules. Yeah, Frank. So far, I haven't discussed UMTC. Well, okay, so the first instance, okay, I know how to realize all UMTC with zero central charge. Okay, so this comes down to the question. So because all of these UMTCs are described by Drinfeld center, you have gapped edge mode. And all this set of UMTC, you can realize them with a string net construction. So you have this proper lattice model, which gives you all possible UMTC with zero central charge. That's point one. Now, when you have a chiral, when you have chiral theory with non-vanishing central charge, I don't know any toolbox like stringnet which allows you to build any of them. It doesn't mean that it does not exist, but there is no known toolbox. And this is certainly, this would be the most valuable progress in the field, is to have some microscopic lattice model which can engineer any chiral phases. And then we would have any UMTC. But for the moment, I don't know anything like that. No, but we have already some models which realize chiral phases, like ICTS honeycomb model. If you are in the isotropic point or something like that, you gave it out. You have an Ising phase. It's a chiral phase. It's described by a UMTC. And this is a very nice microscopic model where you have exactly a UMTC describing that. But the question by Frank was, do we have a way, a tool or a proof that we can realize any of them? I don't know. Where in? A billion one, yes. A billion one, yeah. I think Frank had in mind, not a billion, yeah. Yeah, for a billion, we have many tools.
Can I ask a question online?
Yeah.
I'll go ahead.
Yes.
Yeah. So could you just elaborate on the larger scope of this approach? What are the new results that come out of it, and how does it what new things can come out by this kind of formal approach?
So the thing is that, again, for the moment, all I did is to discuss fusion category. But then tomorrow I will introduce this notion of braiding, and then we will end up with this notion of UMTC, so unitary modular tensor category. And the claim is that each UMTC corresponds to Anyon theory. Okay, so in other words, if we can classify all possible UMTC, we can classify all Anyon theory, or in other words, all topological quantum phases in 2+1 dimension. So that's the goal. And so many people are working in this field. The classification is still under progress. So far, I think that all possible UMTC with a rank lower than 12 are known. And there are already a lot of them, something like 609. Well, mathematicians are still trying to do the full thing. I don't know if full will ever arrive. But the goal is really to classify all possible topological phases of matter. And this can be kind of useful because suppose, for instance, you have a microscopic model, like what Frank was asking for, and you have some good reason to believe that the ground state or the low energy physics of this system is described by a topologically ordered phase. But you want to know, what is this ordered phase? What is this topological order? And then, okay, we have tools to eliminate some candidates, but then we might still have some different choices. And then if you have the catalog, you can have a chance to find your favorite Anyon theory, which really describe your phase of matter. That's the goal.
Thank you so much.